Welcome everybody to Algebra 1, Section 4.2, Equations as Functions, Graphing by Function Table. So let's talk about equations. Functions, as we noted, were relations where the x values didn't repeat, where every input went to exactly one output, every x went to exactly one y. And so functions can also be represented by an equation or a rule. An equation or a rule. And we'll often see them actually expressed or represented by an equation. Now the equation will generate ordered pairs, like we talked about in section 1, x comma y's, okay? And how that happens is by taking an input, the x value, that results in a certain output, the y value. So I likened a function last time in 4.1 to being a vending machine. You put something in, you get something out. You push a code, you get the item out. And in the same way, we put an x value in, we get a y value out, or an f of x value out, as we'll talk about in 4.3. But for now, let's just talk about this next bullet point. The graph of an equation is a set of all these ordered pairs, which often forms a line or a curve of some sort, which is what we'll be seeing today. So an example of a function, once again, think of it as where you put the x value in, you get the y value out by completing some sort of math here. And so the x value is what we call the independent variable. And the reason why it's independent is because it doesn't depend on anything. You get to pick whatever it is, and you can pick whatever numbers you want, truly. Although today, on our when we're having these x values, we're going to have them pre-picked today. But technically, you can pick whatever x values you want, and you just plug them in. Now, the y values, whatever y values you get out, changes or depends based upon the x values you put in. If you put in this x value, you get out that y value, whereas if you put in a different x value, you get a different y value out. Very similar to the vending machine. The item you get out depends on what code you put in, not the other way around. So y is considered to be the dependent variable. So here our instructions are to graph these by using a table. And so we have this equation, y equals x plus 4, and this is actually a function. And what we're doing here is we're told that we have these 4 x values that we'd like to graph. But in order to graph them, we need to know their corresponding y values that would make them an ordered pair. And so what we're going to do is we're going to plug this x value in, get a y value out, and then do the exact same thing with the next x value, the next x value, and the last x value, where you keep plugging something in, getting something out. And how we do this is we replace or substitute x with the numbers. So we're going to start by substituting it in with -5. So y equals -5 plus 4. Everything else stays the same. The y stays the same, the equal sign stays the same, the plus stays the same, and the 4 stays the same. The only thing that changes, instead of x adding with 4, we have -5 adding with 4, because -5 is replacing x because it's the x value we're using. And so now we just evaluate or do the math, doing order operations. And -5 plus 4 is -1. Meaning when you plug in -5 for x, you get -1 out for y, and that creates this ordered pair. And then we move on and do the exact same thing with the next ordered pair. So you plug in -4 now, and you get y equals -4 plus 4, which results in y equaling 0. And once again, you just keep doing the exact same thing with the next values. So for example here, y equals -2 plus 4, which ends up being y equals 2. And last but not least, we're going to plug in the x value of 0. I love plugging in 0 because 0 is an easy number to work with most often. And so 0 plus 4 is 4. And now I have this table, and we know that once we have tables, we can graph these points. And so I'm going to plot these points. I'm going to start out with -5, -1, -4, 0, -2, 2, and 0, 4. And obviously we skipped some points there, but you can notice that -3 would appear to be right here, and -1 would appear to be right here. And that's exactly what would happen had you plugged in -3 and -1. And because what happens here is this is actually ends up being a straight line that connects these. And because you could continually plug in more and more and more and more and more x values and get more and more and more and more and more and more and more x value or y values out, rather, you can plug in more x values to get more y values out. We put these arrows on the line, showing that it could go forever. I could plug in the x value of 20 and get the y value of 24 out, and that would go clear off the graph. It'd be like, way, if my iPad lets me zoom out, way up here for comparison, or probably actually closer to like way over here for comparison, but it would still continue to go this direction, eventually reaching that coordinate. And the same thing's true down here, that you could plug in an extremely negative number, which it would eventually reach as well. And that is how we graph these functions. So we plug these x values in to the function, get these y values out, and then now we make these ordered pairs in the table and graph it with arrows on each end. So number 2, if we follow the same process but plugging in these four numbers of -4, 0, 4, and 8 into the function y equals 3/4 x minus 2, we're going to have y equals 3/4 times -4 minus 2. Now, I'm going to put that -4 over 1, so now I have a fraction times a fraction, so I can reduce the 4 and -4 to become 1 and -1, and I get y equals -3 minus 2, which results in y equals -5. Now I proceed and do the next one in the same exact manner. Y equals 3/4 times 0 minus 2. And 0 times anything is 0, which is quite convenient, because now we just have y equals -2. Next, as I plug in 4, I have y equals, let me stay consistent in my coloring here, y equals 3/4 times 4, or 4 over 1, minus 2. The 4's reduce, and y equals 3 minus 2, which results in y equaling 1. And last but not least, I'll do it over here, because I'm out of room kind of on the right there, if I want to do a problem later. So y equals 3/4 times 8, or 8 over 1, minus 2. The 4 and 8 would reduce to 1 and 2, giving us y equals -6 minus 2, which results in y equals -8. Oop, I wrote -8 instead of -2 here in the orange, anticipating a little too early the result. I did some math wrong here. Let me look for 1 second. What did I do? Oh, silly me. That should not have been a -6. Let me undo that and redo that. That should have been a +6 minus 2, which is 4. And so now we have these 4 ordered pairs that we're going to go ahead and graph. Noting that 8, 4 goes off the graph, and so we're just going to ignore that point, actually. Oh, but I did 4, 0 instead of 4, 1. That explains my lack of getting a straight line. I wasn't getting a straight line, and I was like, what's going on here? And that is our line. Now you'll notice here that these numbers all increase by 4, and that's not a coincidence here that that was selected on this problem, because we're working with a fraction that we're going to be multiplying with. We wanted each of these numbers to reduce well with the fraction, and all of them did. None of them ended up having fractions as part of the answers, which is convenient. Now you could pick numbers that would still result in fractions, and that's not wrong. It's just going to create a little bit more work for you to have these fractions, that's all. But since we can pick numbers, it's best for us to think about, okay, what numbers are going to be easiest for us, so we can make life easier and our work less complicated, needlessly complicated, may I add. And the reason these numbers were picked then is because they're multiples of this denominator. Had you picked a number that was not a multiple of that denominator, such as 2 or 3 or 5 or any other number that's not a multiple of 4, then those numbers would not reduce completely with that, leaving us still with a fraction. Number 3 here, y equals 3x. So we have these 4 x values selected already, -2, -1, 0, and 1. So I'm going to start plugging these in. And as I plug them in, I have y equals 3 times negative 2, which gives me y equals negative 6. Then I'm going to go and plug in y equals, negative 1 for x, so 3 times negative 1, which is just y equals negative 3. Now as I plug in 0, 3 times 0, that one's nice. I always like plugging in 0. I get y equals 0. And then last but not least, as I plug in 1, I get y equals 3 times 1, which is also not a bad number to plug in, because 1 times any number is just the other number. And so now as I plug these in, I end up getting the following order pairs. Connect these. They should make a straight line, otherwise you did something wrong, like I did in the last one for a moment before correcting where the point was on the graph. And then draw the arrows on each end to call this our line. On to number 4, plugging these in. Notice with the fraction here that we're multiplying with x, we have multiples of 2, multiples of this denominator. That's very purposeful, like I mentioned a moment ago. So here we end up having y equals, I'm going to pick a different color than purple this time. I'm going to change it up. We're going to do, let's do green to start out. So y equals negative 3 over 2 times negative 2 plus 2, or this negative 2 could be over 1 as well. And so now as these 2's reduce to get 1 and negative 1, so y equals 3 plus 2, and y equals 3 plus 2 is y equals 5. So now I move on to the next one, and I continually plug these in and continually get my new answers out. And so I'm going to go ahead and let you finish this, and I'm just going to tell you what the answers are. So the answers to the next 3, as when you plug in 0, you get 2 out. When you plug in 2, you get negative 1. And when you plug in 4, you get negative 4. If you didn't get those answers, I would suggest going back and double checking your work there, especially paying concern to this negative. So as I plot these points, I have negative 2 comma 5, 0 comma 2, 2 comma negative 1, and 4 comma negative 4. Plotting these and connecting them with the line with arrows. Example 5. Pay special attention that this is a negative x, so I'll showcase a couple of these so we can see what this looks like. So we'd have y equals negative of negative 3. 2 negatives there. 2 negatives here. One negative is from this, that's the one outside the parentheses, while the other negative is from the x value itself, inside the parentheses. And so this would end up resulting in 2 negatives in a row, becoming a positive. When you have 2 negatives with no numbers between them, they become a positive, and 3 plus 1 is 4. And the same thing would take hold when you plug in negative 1 as well, so go ahead and attempt to plug in negative 1. So once you plug that in, you end up getting the y value of 2 out, because you have negative of negative 1, creating a positive 1. Now as I try plugging in 0, I end up getting the y value out of, well, go ahead and pause and do this one as well, and I suggest you go and do the x value 4 as well. So we end up getting 0 comma 1. And then I'm going to showcase when you plug in 4. Hopefully you've already attempted this one. When you plug in 4, you only have the x value that was from this outside the parentheses. But now the number you plugged in is negative, so it remains negative as you add it to 1. And we end up getting negative 3 because of that. So now we go and plot these points, negative 3 comma 4, negative 1 comma 2, 0 comma 1, and 4 comma negative 3. And you notice there's a lot of gaps there, but they still follow the same line all the way down. Now we're on to number 6 here. Plugging in these. Once again, noting that, hey, since we have a fraction multiplying with our variable, these are all multiples of the denominator. Not a coincidence, that makes our life easier. You could pick different numbers. It's just going to make us have fractions, which we don't prefer to deal with typically. So go ahead and work on plugging each of these in here. Noting that once again there is still a negative here, so a negative times a negative would create a positive, for example. So you end up getting the y values out of 2, 1, 0, and -1 when you plug in -3, 0, 3, and 6 respectively. So now as we plot these points, we end up getting the following. Moving on to number 7. 7 through 14 all have the same directions, which are really basically what we just did, actually without the graphing, and only one less x value to plug in, and written differently, but we're still going to be plugging x values in, getting y values out all the same. So here we're told that we're given a domain and a function and to find the range. Well, reminder that domain are the x values and the range are the y values, aka we're given x values, find the y values, which is exactly what we just did on these tables, where we plugged x values into the function, got y values out of the function. But now instead of writing it as a table and graphing, we're going to be writing it as a range, r colon or range colon, with braces around it. That's the only difference, and if you happen to get the same y value twice, which you won't on any of these problems, then you would just not repeat it, as we don't repeat any numbers with domain or range. And we do list these least to greatest, so whatever y values you get out, make sure you list them least to greatest. Moving on to actually plugging them in. So how you plug them in is the exact same as before, so I'll show this first one on number 7, where you plug in the x value of 4. So it'd be y equals 4 minus 5 instead of x minus 5, and that would result in the y value of -1. And so I'm going to write that in my range. The next number I would get is 0. Sorry, try that again. The next number I get is 1, and the next number I get after that is 3. And this does go least to greatest. Now, for some reason, which this will happen, just so you know, that when we plug these in, if this ends up getting a smaller y value than the first one, then I have to switch the order. I have to write this before that, because once again, we want them least to greatest. Go and attempt number 8 on your own, plugging in each of these 4 x values and getting 4 y values out because of it. So as these plug in, they will go least to greatest again, as -1 giving us the lowest y value and 4 giving us the highest y value. And the y values you get out are -2, 1, 4, and 13. Big increase there between 1 and 4, so a big increase between 4 and 13. Number 9. This time, the numbers we plug in will continually decrease here, and that's because of this negative. So as we plug in -2, we actually get our biggest number, and as we plug in 5, we get our smallest number. So -2 would give us 6, 3 would give us 1, and 5 would give us -1. But we still put them least to greatest, so it might be helpful to find all 3 values first, find that y equals 6, y equals 1, and y equals -1, and then write your range, so that way you're not having to erase it and be like, oh shoot, now I have to rewrite it so that I realize it's not least to greatest. So you can find all your y values first, and then put them in your range. Number 10, note that with a fraction multiplying with our variable, we once again have multiples of the denominator. So go ahead and plug in these 3 x values. They will give us y values in a least to greatest order, and we end up getting the y values of -4, 2, and 5 as we work through these problems. If we plug in -10 here and distribute through. I'll go ahead and show plugging in -10 just in case you did not have success with this problem and you're still quite confused about it. So y equals 3/5 times -10, or -10 over 1, plus 2. And this 5 and -10 reduced by 5 to become 1 and -2. And now we multiply straight across, and 3 times -2 on the top of the fraction is -6 over 1 on the bottom, which we don't have to put divided by 1. So we have -6 plus 2, which results in y equaling -4, like we got right here. Under number 11, go ahead and find these different y values, or the range, once again from least to greatest. Here we end up getting the y values out from least to greatest of 4, 7, and 9, noting that they weren't quite in the order we'd expect them to be, with -4 giving us the biggest one. So I'm going to practice plugging in -4 so we can see this. And I get y equals 7 minus 1/2 times -4, or -4 over 1. The 2 and -4 reduce to become 1 and -2, and a -1 times a -2 create a +2, so I get y equals 7 plus 2, which results in y equaling 9, which once again was our biggest y value here on this problem. Number 12, go ahead and plug these in if you haven't already. We end up getting the y values out of 7, 13, and 17. I'll go and showcase that first one again. Y equals -2/3 times -12 plus 9. Put that -12 over 1 and reduce. 3 becomes 1, and -12 becomes -4. And -2 times -4 gives us +8. So we get 8 plus 9, which is 17. The same number we see right there. On to number 13. As we plug in this range, figure out what you get out for your, or don't plug in the domain rather, figure out what you get out for your range. You end up getting the y values -13, 11, and 19. Quite big here, and that's okay. So let's say I go ahead and plug in -3. So I have y equals 7 minus 4 times -3. And -4 times -3 is +12. And so I have 7 plus 12, which is 19, or that biggest number we saw. Try it again. There we go. So far, maybe you're noticing, hopefully noticing, like I tried to point out earlier, that when there's a negative with the x, negative with whatever numbers with the x, that these are not going least to greatest. And we saw that on those three, that they go in the reverse order for the range. So -2 gave us the biggest one, 3 gave us the medium, and 5 gives the smallest. Whereas when the number with the x was a positive number, such as numbers 10, 8, and 7, I missed number 12 being a -1 as well. These end up going in the exact order we think they would, where 4 gives us our smallest, 6 gives us our middle, and 8 gives us our biggest. And that is a consistent theme we'll see with these. So on number 14, because the number with x is positive, that means that this will give us my smallest number, medium number, and biggest number out for a range. And so go ahead and find the range. The range here is -7, -6, and -2. And so to practice plugging in, I'll plug in the first one again. Y equals 1/4 times -8, or -8 over 1, minus 5. Let me rewrite that 5 slightly. There we go. And the 4 and 8 reduce by 4 to become 1 and -2. And 1 times -2 gives us -2 minus 5, which is -7. The first number we see. Moving on, let's recap here as I remember to rotate this page. There we go. There are 5 different ways to represent relations. One is as ordered pairs, tables, mapping diagrams, equations, and graphs. Now, each of these that we're going to be covering, this is just kind of a review, no new information on this slide. A review here, all 5 of these are going to be representing different relations. I want to make that key. They're not all representing the same relation here on this problem, on this demonstration, on this visual graphic organizer. They're representing different relations. So ordered pairs is its own relation here in this case, and the domain here, the list of x values, would be least to greatest, -1, 0, 2. There was no repeating anyway, so you don't have to worry about that. Whereas for the range, the y values from least to greatest would be 2, 5, and 7. Is this one a function? Yes, because no x values repeat. Let's turn our attention to the table. The table, once again, recapping the domain and range. The domain, once again, are the x values listed from least to greatest with no repeating, which comes in key here because it's just -2, 0, 3, no second 3. And the range is -4, 1, 2, and 6. Is this one a function? No, it's not a function. Why is it not a function? 3 repeats, or 3 goes to both 1 and 6. On to the mapping diagram. We have these arrows, but our domain and range are nice here because this is just the x values and y values listed in the exact same manner domain and range should be listed in, least to greatest with no repeating. So -7, 0, and 3, and the range is 1 and 2. Is this one a function? Well, we have 2 x values going to the same y value. But that's no matter, that's still a function. That just means it's a popular vending machine item. So yes, it's still a function. We can have the y repeating. We just can't have the x repeating. An equation. This is one we haven't seen one of these yet, but regardless, it's still an equation. Y = x squared minus 1. And we have seen the graph of this. If you want to use a graphing calculator here. We saw the graph when we were doing the domain and range back in section 1, I should say. And so here, what would happen is this graph would look something like this, with that bottom point being at y equals -1, x equals 0. So the domain and range, the domain is negative infinity to positive infinity, forever left to forever right. Or you could also rewrite it as the all real numbers double-lined are. The range is the lowest point of -1 going up forever to infinity, with -1 getting a bracket because it's not an open circle. It could also be written as y is greater than or equal to -1. Is this one a function? Why, yes, it is. How could you know? It passes the vertical line test. No vertical line would ever hit more than 1 point. And the last way is a graph. And while an equation helps us get the graph, a graph is still a different way to represent it. So the domain here, from farthest left to farthest right, and everywhere in between with no breaks or gaps, we end up having the domain of -4, 1, with both being brackets. Or you could write it as -4 is less than or equal to x, which is less than or equal to 1. Range can be written in a similar manner. The lowest y value of -2, the highest value y value of 3. So -2, 3, both with brackets. Or the compound inequality, -2 is less than or equal to y, which is less than or equal to 3. Is one a function? Why, no, it's not. Why is it not? Well, it fails the vertical line test. There's many vertical lines that would hit more than 1 point. And so it fails this vertical line test. And so that is a great graphic organizer that showcases you 5 different ways to represent relations. And this wraps up Algebra 1, Section 4.2.